All right, welcome to the deep dive. This time we're diving deep specifically for you into momentum and impulse based on all the materials you sent us.
Yeah, you've given us a great starting point, and we're going to really get to the core of these concepts, momentum, impulse, and how they're all linked.
So first things first, what exactly is momentum? I think we all have a sort of intuitive sense of it, like it's harder to stop a moving truck than a moving bicycle, right?
Exactly. Momentum is essentially a measure of how much oomph an object has when it's moving, kind of like its resistance to change in motion.
Inertia in motion.
Yeah, exactly. And more formally, as your materials laid out, momentum, which is often represented by the letter P, is simply the product of an object's mass, m, and its velocity, v, so P equals mv.
Okay, straightforward enough. But it's important to remember that velocity isn't just speed, right? It's speed and direction.
Absolutely, and that makes momentum a vector quantity. It has both magnitude, how much momentum, and direction. And the standard unit for momentum, by the way, is kilogram meters per second. That's kilogram ales.
Which makes sense because it combines kilograms for mass and meters per second for velocity. So, like you said, a massive truck moving slowly can have a huge amount of momentum.
Absolutely. Think about it. A heavy train moving slowly can have a lot of momentum, just like a tiny bullet moving super fast.
Right, both can be really hard to stop. Now, what happens when that motion changes?
That's where the idea of change in momentum, or delta P, F type P, comes in.
Delta P, yeah, I remember that from the materials.
So F type P is simply the final momentum of an object minus its initial momentum. So L type P equals PF minus pi.
Okay, and if the object's mass doesn't change, which is often the case, then the change in momentum is all due to the change in its velocity.
Right. In that case, L type P equals m times n type v, or m times the quantity Vf minus v.
And I guess that's where the whole vector thing comes in again, right? Because if an object changes direction, even if its speed stays the same, its velocity has changed.
Absolutely. And that means its momentum has changed too, even if the speed's the same. Like if a car is driving north and then makes a U-turn and starts driving south at the same speed, the change of velocity, and therefore the change of momentum, is actually quite significant, double the initial momentum, actually, and in the opposite direction. So you got to be really careful with those positive and negative signs.
Makes sense. Now, can momentum ever be zero?
Absolutely. If an object isn't moving at all, if its velocity is zero, then its momentum is also zero, no matter how massive it is. A parked car, a book on a table, a sleeping cat, they all have zero momentum.
Okay, I see. So we've got momentum and we've got changes in momentum. But what about when multiple objects are interacting with each other?
That's where things get really interesting, and it leads us to one of the most fundamental principles in physics, the conservation of linear momentum.
Okay, I remember seeing that term a lot in the materials. What exactly does it mean?
Well, it means that in a closed system, that is, a system where no net external forces are acting, the total momentum of that system remains constant.
So no matter what's going on inside the system, collisions, explosions, whatever the total momentum before is equal to the total momentum after.
Precisely. The momentum might be distributed differently among the objects within the system, but the total amount of momentum stays the same. It's represented as SPI equals peace. The sum of the initial momenta equals the sum of the final momenta.
Okay, now I'm starting to see how this ties into those three scenarios from the materials. You know, the ones with two objects.
Exactly. And those scenarios are great illustrations of conservation of momentum. The first one is when you have two objects that collide and then bounce off each other. Think of billiard balls hitting each other on a pool table.
Right, or maybe two cars in a fender bender where they kind of bounce off each other.
Perfect examples. So before the collision, each object has its own momentum. After the collision, they each have new momenta, but the total momentum of the system remains the same.
Assuming we can ignore friction and air resistance and all those messy real-world things.
Right, always assuming an idealized system. But the principle still holds. Now, the second scenario is when two objects collide and stick together. Think about two train cars coupling together, or a football player tackling another player, and they both go down in a heap.
Okay, so they become one single object with a combined mass.
Exactly. And the total momentum of that new combined object is equal to the sum of the momenta of the two original objects before the collision.
So even though the mass and the velocity of that final object have changed, the total momentum stays the same.
Precisely. And the third scenario is sort of the opposite. It's where you start with a single object that breaks apart into two or more separate objects.
Like a rocket launching and separating from its booster stage.
Perfect example. Or think of a firecracker exploding, or even a nucleus undergoing fission.
Okay, and the total momentum before the separation has to equal the total momentum of all the pieces after the separation.
Exactly. And that's how we can calculate, for example, the speed of a rocket after it jettisons a stage, or the recoil velocity of a gun after firing a bullet.
Okay, that's really cool. Now, let's shift gears a bit and talk about impulse.
Impulse is closely tied to momentum. Basically, impulse is what causes a change in momentum.
Okay, so it's not the change itself, but the cause of the change.
Right, it's like the push or the kick that gets things moving or changes their motion. And formally, as your materials explained, impulse, which is often represented by the letter J, is the product of the net force acting on an object and the time interval over which that force acts. So J equals net times delta T.
And delta T is the change in time, or how long the force is applied.
Exactly. And as your source has highlighted, a key point here is that impulse is also equal to the change in momentum of an object. So J equals delta P.
So if a large force acts for a short time, it can have the same impulse and therefore the same change in momentum as a smaller force acting for a longer time.
Precisely. That's the key takeaway. And like momentum, impulse is also a vector quantity. It has both magnitude and direction. The direction of the impulse is the same as the direction of the net force that causes it.
Okay, I see. And the units for impulse are Newton seconds or kilogram meters per second, since it's equal to the change in momentum. Now, what about that equation I saw in the materials, mnet equals delta T? That looks familiar, but I can't quite place it.
Yes, that's Newton's second law of motion, but expressed in terms of momentum. It's a very important relationship.
It shows that force is the rate of change of momentum.
Exactly. A large net force means a rapid change in momentum, while a smaller net force produces a more gradual change.
So if we want to achieve a certain change in momentum, we can either apply a big force for a short time or a smaller force for a longer time. Like to move a heavy box, I can either give it a big shove or I can push it steadily for a while.
Perfect analogy. And this principle has some really important practical applications.
Especially when it comes to safety,
You
right?
got it. Think about safety features in cars like airbags, seatbelts, and crumple zones. They're all designed to increase the time over which a person's momentum changes during a collision.
So instead of coming to a sudden jarring stop, which would mean a huge force, the impact is spread out over a longer time.
Exactly. And because impulse equals force times time, if you increase the time, you can decrease the force for the same change in momentum. That's why those safety features are so effective in reducing injuries. By extending the time of impact, they lessen the force on the occupants.
Makes sense. So are there any other real-world examples where this impulse-momentum relationship comes into play?
Tons of them. Think about sports. In baseball, when a batter hits a ball, the bat exerts a large force on the ball for a very short time, resulting in a large change in the ball's momentum.
So the impulse delivered by the bat causes the ball to go from basically zero velocity to flying out of the park.
Exactly. And the same principle applies in tennis, golf, soccer, pretty much any sport involving hitting a ball or an object.
Or in martial arts like breaking boards or bricks, the key is to deliver a large impulse in a very short time to generate enough force to break the object.
Right, and think about landing after a jump. If you land stiff-legged, your momentum changes very quickly, small delta, which means a larger force on your body. But if you bend your knees as you land, you extend the time over which your momentum changes, reducing the force.
Which is why it's so important to bend your knees when you jump. It protects your joints from those high-impact forces.
Absolutely. So as you can see, impulse and momentum are not just abstract concepts. They have practical implications in countless situations.
Okay, that's a great overview, and we've just scratched the surface. There's so much more to explore. But first, a quick recap of the main points. We define momentum as mass in motion, impulse as the change in momentum caused by a net force, and we talked about the conservation of momentum in closed systems. We also covered those three key scenarios for momentum conservation: colliding and bouncing, colliding and sticking, and systems that start together and then separate.
Right, and we dove into some real-world applications like safety features in cars and how athletes use impulse to their advantage in sports.
So here's a final thought for me to chew on. Think about how the concept of momentum applies not just to physical objects, but also to things like social movements or trends in technology, or even your own personal goals.
Ooh, I like that. So a small but persistent effort over a long time can eventually create big changes.
Exactly. It's like that saying, slow and steady wins the race. Where can you apply a small but consistent force over time to build momentum towards something you want to achieve?
That's a great takeaway. Thanks for joining us for this deep dive into momentum and impulse. We hope you found it insightful.
Until next time.